Hello. Today we are going to be talking about synthesizer electronics. A load of stuff over the years that I've learnt that I'm going to tell you. We're going to do it a little bit different, and obviously I can't tell you everything in one video, so each of the videos is going to have a focus at the start, but then we're just going to go off on a journey of exploration, see where it takes us, and you will come away at the end, hopefully, with a load of new knowledge. And even if you're quite experienced in this kind of thing, I think it should still be quite interesting and entertaining for you. Today's focus is going to be on resistance. If you take a look at pretty much any electronics, you're going to see resistors. Little blue through-hole resistors with all the coloured bands on like these, or tiny weeny little surface mount ones that get soldered on by robots. But there are loads of different shapes, sizes and types of resistor. I mean, look at this one. This is a 12 mega ohms resistor. That is a big boy. This one here is made out of carbon, and this ceramic one here is called a dog bone resistor. Why do they call them dog bone resistors? Because they look like dog bones, don't they? And then this one here is a wire wound resistor. Why is that? Because it's made of loads of windings of wire. There's even stuff like this semi-conducting tape that's actually designed for plumbing but can be used to make ribbon controllers. Bulbs, like this massive one out of a projector, or this one that came out of the gun sight of a Spitfire. Even they are a type of resistor, and they have a special quality that we'll talk about later. Basically, some materials are good at conducting electricity and some are bad at conducting electricity, and that's due to their resistance. Of course, even air has resistance, and that's why you have things like these vacuum tubes, like this cavity magnetron. Pretty rare to see example of an early radar device. It sucked the air out of here so that it can all resonate inside these cavities, and this cathode ray tube. You suck the air out of that so that the electrons getting shot by this electron gun at the back can travel all the way unimpeded to the phosphor screen here, where you can draw images. So some of these resistors are better in certain situations, and there's going to be a supplementary video to this one on the Patreon, which is going to cover all those technical details that you're going to want to know if you're selecting these components to be in your circuits. Stuff like tolerances and whether these things are in certain E-series of suggested values and stuff. It's all going to be really useful. I'll remind you about that again at the end of the video, but we're going to concentrate on what you can do with these resistors, because that's much more fun, right? And that's the whole point. If you think about it, everything has resistance, including you, and conversely, everything has a certain amount of conductance. And so if you force electricity through something fast and hard enough, everything can be turned into a wire. And there's a clever bloke called George Ohm who worked out the relationship between resistance and voltage and the flow, the current of electricity through an object. It's called Ohm's Law, the theorem that he came up with, and it's absolutely fantastic, and one of the things that you're going to be referring to a lot through designing synthesizers and stuff. Now, I will warn you, we're straying here into the realms of algebra, but trust me, it's bloody clever and amazing. So this is the formula for Ohm's law. It's the relationship between voltage, measured in volts, current, measured in amps, and resistance, measured in ohms. And if you want to measure that resistance of something in ohms, you can use a multimeter, like this beautiful old British Railways avometer. This right here is the symbol for ohms. There it is on my more modern multimeter. All I have to do is take the two probes, put them either side of the resistor, and it will measure the resistance between those 2 points. Now, you see that little K there before the ohms symbol? That is kilo ohms. So that means 1,000 ohms. So this says 4.54. This is 4.54 thousand ohms, kilo ohms. And similarly, if you see an M, that means mega ohms, as in millions of ohms. And for values like this, 470 ohms, you might actually see it written like this, 470R. It's also common practice to put the kilo ohms symbol where a decimal point may be. That's just so that it's less confusing on a tiny silkscreen on a PCB. So this would be 4.7 thousand ohms. So I suppose at this point I should probably explain to you the difference between amps and voltage and resistance. I brought you to a nice setting to do it by the banks of the Flussweser in Bremen in Germany, home country of George Ohm. I've not come here just for the video, but anyway. So where were we? Oh yeah. So there's an analogy of to help you understand voltage and current and stuff. It's not perfect, but I think it illustrates the point. You've got to imagine, right? So I've got a bucket, right? I've got a bucket. It's full of water. As I raise the bucket up, right, you can think of the gravity kind of pulling the water towards Earth as a kind of analogy for voltage, right? And just because there's a voltage, just because there's a difference in voltage, doesn't mean that there's any current flowing. So in our analogy, we've got a bucket full of water, right? And there's a stored amount of energy in the gravity that has a potential to pull that water down to Earth. But what's stopping it? The bucket, the material of the bucket is stopping the water flowing down, right? So that is the resistance in the circuit, right? There's a voltage potential for the water to flow, like current, but the resistance is stopping it. So if I tip the bucket, I'm decreasing the resistance, and the more I tip the bucket, the more the water is able to flow, and that volume of water flowing is the current. And if you can imagine you're on the moon, there's less gravitational force pulling that water down. It's the same kind of thing as if you had the same amount of resistance but less voltage. Therefore, less current will be flowing. And you can see here that if you know the value of 2 of the 3, you can rearrange the equation to work out the third. Now don't panic, there are free online calculators, so you don't have to do math. Hallelujah! Enough theory, let's talk about how that is all useful. One of the most common things you're going to want to do with a resistor is use it as a current limiting resistor with one of these things, an LED, a light emitting diode. It's a blinky thing, and if I just hook it up to either side of my power supply without a current limiting resistor, oh dear. Oh, I did the sparks for effect, of course, but you get the point. It blew up, and that's because it got too much current through it and it heated up to the point of failure. So how do we protect our LED? We add a resistor in series with it. So how do I find out how much current an LED like this can handle? What I could do is look in its data sheet. It tells you all of its characteristics. And you'll see there that its maximum forward current is 30 milliamps. Anything above that, and it's gonna blow up. Around about 20 to 30 milliamps is typical for an LED, really. This is our hypothetical circuit. This is our LED. This is our current limiting resistor. And on this side, we've connected it to positive 12 volts. And over here, we've connected it to ground, or 0 volts. So we can use our calculator here to work out what size resistor we need to protect our LED. Now, I wouldn't blame you if you just put 12 volts, the supply voltage, into that top field. But we need to talk about another characteristic of LEDs, their forward voltage drop. Yeah, and so if you look up in the data sheet, you will see there is a number for the forward voltage of the LED. In our case, this is 1.85 volts. Basically, and we're going to talk more about this in a specific LED video where we talk about semiconductors and exciting things. Basically, what happens is that the LED only turns on after a certain voltage threshold. In our case, this is 1.85 volts. And so what we need to do to calculate the current draw of the LED, of which a factor is the voltage across the LED, we need to subtract that voltage drop from the supply voltage. Okay? I know it's a bit of a weird thing to get your head around. It will make more sense after we've done that LED video. A lot of these things in electronics, it's good sometimes to just accept that that's the way it is, not have to think too much about why, and just move on with your life. So we're going to subtract that forward voltage drop of 1.85 volts from our hypothetical power supply of 12 volts, which would be a typical thing in a Eurorack setup, for example. So enter 10.15 volts. Then we're going to enter the 30 milliamps, the maximum amount our LED can take. Press the button, it does the math and tells us that anything above a 338 ohm resistor will do the trick. They don't make 338 ohm resistors, so you round it up to the next available value. In reality, you're going to want to give yourself a little bit of a margin. We'll stick a 1k in there, and he's happy as Larry. We'll talk more about LEDs in a future video, but there is obviously a relationship between the current that you put through it and the brightness. The more current, the brighter the LED will be. Now, I've put the resistor before the LED in this circuit, but it could have gone after. As long as it's between the 12 volts and ground, it will be limiting the current that is flowing between that voltage difference and through our LED. Incandescent bulbs like this don't actually need a current limiting resistor, and there's a really interesting reason why. When the current flows through the filament of this bulb and it heats up and produces light as a byproduct, the metal actually increases its resistance as a result of that heating. And so you can see how as you put more current, the resistance of the filament increases and it self-regulates so it doesn't burn out. Really, really interesting property, and they actually harnessed it in a special type of bulb called a Beretta with an iron filament, and this was a really early example of a voltage regulator. You can see written on the glass, General Electric Company Resistor 300 ohms. The first piece of test equipment that Hewlett-Packard made was a valve-based oscillator, and the pitch of it was stabilised by a light bulb. Now, if we look back at our LED datasheet, you will see underneath the DC forward current, which is direct current, a constant current running through the LED, there is a peak forward current. 155 milliamps is a lot more than 30. And if you look at the little note, it tells you that this is the amount of current that the LED can handle in a pulse of 0.1 milliseconds. And this points us to something that is really important to factor into all of these calculations, which is time. So something like a static charge that you might pick up and get a little shock from, it can be really, really high voltage, but it's for a very, very short amount of time, so it doesn't do you any harm. And there's a measure for this that's commonly used with resistors to make sure that it can withstand the power that's going through it. It's called the Watt, named after James Watt, you know, the bloke with the steam engines. And it can be a bit confusing to get your head around at first, but basically it's a measure of power over time, so joules per second, and it's kind of analogous to miles per hour. You know, you can know the distance, you can know the time. This is a combined measure that's quite useful, especially in selecting resistors. If you know you're going to have a certain amount of power going through it, you want it to be a certain wattage. Very handily, our online Ohms Law calculator can also calculate watts. Ohm's Law isn't only useful for calculating the current draw of LEDs, you can use it to check whether ICs or op-amps can also supply or sink enough current. This is a 4017 chip, popular with Synth DIYers for making sequencers, and one thing you might want to do with this is use it to light up an LED. And now once you've calculated how much current the LED is drawing, you can look at the datasheet of the 4017 and see whether it's capable of supplying that amount of current. Now there's also a distinction to be made between sinking and sourcing. So sinking is when the leg on the IC or chip or whatever is acting as the negative side of the circuit, sinking the current into it, and conversely sourcing is when the IC is acting as the positive side of the circuit and supplying the
voltage.
And a side note, that is true in the conventional way of thinking about current flowing from positive to negative, but actually in reality what happens is electrons flow from negative to positive. What happened was, way back in history, they got it wrong and started thinking of it in the conventional model, what we call now, and then discovered they were wrong, but it was too late. They'd already settled on that way of thinking. It does work quite well, to be fair, but yeah, electrons flow from negative to positive, not the other way around.
So let's take a look at the CD4017 datasheet. We can see that when it's powered off of a 15 volt supply, the pins, when high, can source typically around 6.8 milliamps. And so we know if we want to power an LED off one of those pins when it goes high, we want to make sure that the LED is not drawing more than 6.8 milliamps.
So let's give this a go. The first thing that we need to do in our Ohms Law calculator is put in the voltage difference across our circuit. The output pins of our 4017 chip are digital, so that means that they have two possible states. They can be high or they can be low. When they are high, that means that they're connecting to the positive power supply rail of our chip, and when they're low, they're connecting to the negative power supply rail. So we are powering our 4017 chip off of 15 volts, which is quite common for synthesizer circuits, but if you wanted to power it from, say, 12 volts, which might be more typical for a Eurorack supply, then you need to be aware that those current ratings are going to change with the supply voltage, and you should check in the data sheet what range of voltages, the minimum to maximum, that your chip can be powered off. It differs for every integrated circuit. But we are connecting 15 volts to our positive power pin, sometimes referred to as VCC or VDD for really boring reasons that you really don't have to worry about, and we're going to connect the negative side of the power supply, so that's 0 volts or ground, to the negative power pin, sometimes referred to as VSS or VEE. So we know when those output pins go high, they're going to go to nearly 15 volts. So this is an important point because not all integrated circuits have the capability of swinging all the way to their power supply rails. This applies to digital outputs like this, but also to analog outputs. So you might see some operational amplifiers referred to as rail to rail. That means that they have the capability to go all the way to their power supply rails. Our 4017 chip's pretty good, so we're going to put 15 volts minus, remember, that voltage drop over the LED of 1.85 volts, so that's 13.15 volts. Put the 6.8 milliamps the chip can handle into there, press the button, it does the math, and it will tell us that anything over 1.9 kilo ohm resistor will do the trick. Again, you want a little bit of a margin, so round that up to like 2k or even better 2.2k for reasons that you'll know about if you watch the supplementary Patreon video to this, and that will give us a decent brightness of the LED without straining the chip. Lovely. In my experience, you can push things a little bit harder than what they say in the data sheets a lot of the time, and really that's just got to be a judgment call of experience. And really, you know, if you're selling a product, you don't want to be going over the datasheet specs because, you know, if you sell someone something and it breaks, that's not good. But if you're just making a one-off thing for yourself, you know, do what you want. I really want to stress at this point that I could go on and on and on and talk about things like, I don't know, voltage droop or something, and it might be useful, but probably not. And got to remember that the main thing about synthesizer electronics is meant to be fun, and you can get a really long way thinking about electronic components like Lego bricks. You know, don't get put down and worry too much about what you read on forums or in, I don't know, electronics engineering journals and stuff, because so much of that stuff, it doesn't apply to synthesizer electronics. It's when you're designing a piece of medical equipment that somebody is depending on for their life, or some kind of really high frequency radio antenna or something. That stuff doesn't really apply to synthesizer electronics. It's more like an art than a science, you know, and a bit of imprecision is musical. Remember that, yeah? So don't worry, and don't let all of that chatter on the internet be a barrier to entry. When you reach a practical problem and something doesn't work, which will happen, that's a good signal then to go back in and research and top up your knowledge as you need to. You don't need to learn everything off the bat straight away. Just do it as you need. Don't think for a moment that I'm at the end of my journey. Not at all. I have so much more to learn. Cool, I think we're just getting warmed up now. Let's have a look at variable resistors.
This is quite the collection, if I do say so myself, of light-dependent resistors. So you can guess from the name probably that these vary in resistance depending on the amount of light that falls on them. Pretty cool. That interdigital pattern is the most efficient way to maximise the surface area of the sensor.
And you can use those to make a thing called a vectoral, which can replace a fixed resistor within a circuit. It's a really easy way to add voltage control. We're going to talk about that a lot more in another video. Did you know that old telephones like this work because of variable resistors? If I unscrew this, you can see the carbon microphone capsule, and inside there's granules of carbon with a diaphragm on top, and the pressure of the air when you speak moves that diaphragm, compresses the granules, which increases the surface area between them all, which decreases the electrical resistance, and so your voice modulates the current, and that can be replicated at the other end as a waveform through another variable resistor. The exact same thing. It's the exact same thing in reverse. Speakers and microphones, pretty much the same.
When you think of a variable resistor, you probably think of something like this with a knob on the top, and you turn it and it can vary the resistance and turn up and down the brightness of an LED, for example. So let me explain to you what is happening inside of this component. It has a ring of conductive material. Now this is graphite, which is conductive, so I'm going to draw a ring of conductive material. This is the exact same LED circuit as we had earlier. I've just replaced the resistor with this variable resistor that we've drawn here on a piece of paper with some graphite. This lead comes from the power. I'll connect that there. And if I move this lead, which is equivalent to the wiper in one of these things, then you will see that the less resistive material we have between the power and the LED, the brighter the LED will be. Really bright there, dull over here. Now this is a 2-lead device, so this type of variable resistor is called a rheostat, and that differs from a potentiometer, which is a 3-legged device and used for voltage control, whereas a rheostat is used for current control. Let's talk about voltage dividers then and potentiometers. So now you're familiar with the inside of one of these potentiometers. It has a resistive track running around here and a wiper that can connect to any point along that track. The left side terminal is connected to the left side of the track, the right side terminal is connected to the other end of the track, and the middle terminal is connected to the wiper. Let's draw all that out on a piece of paper. So we've got the left terminal here, and that is going across a huge resistive track around to the right side terminal, and in the middle we have the wiper that can move along it. The really cool thing about resistors is you can use them to divide voltages. So what we're going to do is connect a voltage across this resistor. Let's put ground here and let's put 12 volts there. Now if you tap out the middle of the resistor, so it's as if you have two separate resistors of equal resistance, then you're going to get exactly half of that voltage. So you're going to get 6 volts out of this point. If I move that wiper down to a quarter of the way up this resistive track, then you're going to get a quarter of the voltage. So that's going to be 3 volts there. And if I move it up this way to 3/4, then I'm going to get 9 volts. It's all to do with the proportion of resistance on either side of this tap off of the voltage divider. And you don't have to do that with a variable resistor, you can do it with fixed resistors, and you can work it out with online calculators, which is really handy. Now say I have 4 fixed resistors of equal value connected together. Now I can put ground here. I can do 1 resistor, 2 resistors, 3 resistors, 4 resistors, and connect that to 4 volts. At each point in between the resistors, I'm going to step up a volt. 0 volts, 1 volt, 2 volt, 3 volt, 4 volts. This is called a resistor ladder. And obviously you can imagine with different values of resistors, this can get much more complicated. Commonly, potentiometers or voltage dividers are used as attenuators or in mixers. And I would definitely advise going to the Dopefer website if you haven't already, because there's loads of fantastic examples of simple circuits that you can have a go at. It gets a bit complicated when you start considering resistor networks like the delta and Y configuration. And this concept really is at the heart of complex stuff like digital to analog converters, but it all starts with the humble resistor.
And a reminder again, if you want to see the supplementary video to this one, that is over on the Patreon, along with a load of other cool stuff, and you get to see stuff early. I mean, what's not to like? I'll see you over there, yeah? This was by no means exhaustive. Could have talked forever about this stuff, we've barely scratched the surface. And a long video like this, it's probably likely that I've misspoken at points, and I welcome corrections in the comments. It's helpful for other people, and that is the spirit that you should be entering into in the comments section, yeah? No arguing, helpful and kind to other people. So I hope you found that useful, or at least interesting, and not all of these videos are going to be focusing on components, they're going to be focusing on different kind of circuits. I reckon the next one will probably look at designing filter circuits, which is pretty cool, and there's a lot of stuff that we covered today that will set us up for talking about that. Right, now go forth and have fun building synthesizers.